Okay, welcome to Math317 Operations Research Lecture 13. I've been having a lot of meetings with people in the county about possible project opportunities. If you are arrested in Berkshire County in the very near future, say you were working on something for Professor Miller's class to test the district attorney's database system, you can try it. But that is one of the people we may be working with. So, what I want to do today is talk a little bit about how you would actually set up some of the problems that you might want to solve. So we've talked a couple of times about, imagine you own American Airlines or imagine you own a movie theater. How would you actually write down the constraints in such a way that you could actually convert it to a linear programming problem and then solve it? You can, of course, write your own program to implement the simplex method. Is there a need to do that? No, it's out there on the web. And depending on how many variables you have, you might be able to get by with just a simple dinky freeware version, or if you have a really complicated problem, and we've done this in the past, you get an account with IBM and use some of their stuff. So the tools are out there. The challenge is to figure out how do you convert the problem you want to study to something where you can use these methods. So we have talked about real linear programming problems. And real does not mean real world, it means real numbers. There's the joke of the lecture on real simple Lie algebras, which was not simple. Okay? What is the advantage of real over integer? Why do we like real numbers over integer numbers?
They're continuously varying.
They're continuous. We have the possibility of using tools from analysis and calculus. If we have discrete things, it turns out discrete optimization is significantly harder. And unfortunately, the discrete optimal may be very far from where the real optimal is. So we're going to start off with binary integer programming. So when you see binary, what do you think? So are we only allowed to use zeros and ones for binary? Nothing but 0 and 1.
I guess we just see on and off.
On and off, true, false, yes, no, Yankees, not Yankees, the two teams left in the playoffs. Is this a loss to go from real to just binary, to just 0, 1? Is there anything in between all the real numbers and just 0, 1? What could we look at instead of binary? I'm sorry?
Hex, octal, decimal.
Okay, that's a little bit more. But I'm saying right now with binary, we're saying all the variables are in 0, 1. That's it. Is that a little bit limiting? Is there anything in between the whole reals and just 0, 1?
Yes, just the integers.
We could have just the integers. So the real question is it a restriction to lose the integers? So let's say n is an integer. We'll say it's a natural number. I'm not going to worry about sign. I can write the number in binary. I can write this as n as maybe, ak 2 to the k plus ak minus 1 2 to the k minus 1 plus a1 2 plus a0 times 1. So if I give you an integer, I can represent that integer as a tuple of 0, 1 variables. As long as everything is bounded, this is not a problem. So is there really a loss in going from integer to binary? No. It might be inconvenient to code like this. That's fine. And my God, this is not representing now, A0, A1, A2. It's not going to be maybe how much of product one did I buy. This is going to be the 1's unit base 2 of how much I bought. This is going to be the 2's unit base 2. This is going to be the 4's unit base 2 of how much I bought. But we can still do that, and it is sufficient to study just binary random variables. Okay, so there's really no loss in studying just binary. Okay, how many people have seen you're working in base 2 and decomposing numbers? This is sometimes done in high school, and kids typically don't like it. Used to base 10. Right? When you saw log in high school, what did log mean?
You didn't know.
Base 10.
So log meant base 10. And what did ln mean?
Base
It's base e. And now once you go to college, there's no longer ln, log is base e. You just need to get used to what notations people are using. So here, it's not a big deal. As an aside, sometimes these are a pain to program when you have a variable number of for loops. And so I just want to show you a nice programming trick. And again, a lot of times, it's sufficient to just program naively now because we have so many powerful computers at our disposal. You don't need to be as clever. The first computer I programmed in, I think, with the memory expansion, had 16 kilobytes of memory. Okay? You had to be extremely careful in what you were doing in a system like that. So let's say you want to program for x1 equals 0 to, let me see, I think I want to do it to b minus 1 to b minus 1 dot 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 xn equals 0 to b minus 1, but n is a variable. If you were to try to write for loops in your program and hard code this, you wouldn't be able to do this because the number of for loops is going to depend on some parameter n that you pass into the program. Right? If I knew that I only had 5 or 6 or 7 for loops, I could just hard code that. But when the number of for loops is a function of some other part of the program, then it's a little bit more involved. So I'm going to show you one of my favorite programming tricks. It is related to what we were just talking about. Does anybody know how to do this in one for loop? You can actually do a variable number of for loops with one for loop. How many numbers do we have? So how many numbers do we have? How many tuples is what? Not quite b, close. B. Each one goes from 0 to b minus 1.
Oh, so
It's b to the n. Okay? So here's the solution. For m equals 0 to b to the n minus 1, write m in base b, and that's your tuple. So if you write m in base b, then the digits, when you count from 0 to b to the n minus 1, is just going to be your values of x1 through xn. So this allows you to count with your variable number of for loops in one very simple, clean line of code. All you have to do is, once you have your number, you convert the number to base b. And there's a lot of programs that have this already built into their language. So something like this is not a big deal. The last one is, I think we've talked about how to do Sudoku cleanly. Or have we not talked about Sudoku? All right, so let me just do Sudoku really quickly and then we'll go to code. Okay, so Sudoku. Is there anybody who has not done a 3x3 Sudoku? Oh, 9x9. All right, everybody, so if you want to make sure that it's a correct grid, is this an easy or a hard problem?
Easy to check. It's easy to check.
Right, so the computer scientists have a whole theory devoted to problems like this, right? What do we call them in computer science?
Theory of computation.
I'm sorry?
Theory of computation.
But what do you call these types of problems?
NP hard.
NP hard. So they're often hard to solve, but it's trivial to see if you have a solution. Factoring a number we believe is hard. Checking to see if two numbers multiply to a third, easy. Solving a Sudoku could be hard, but checking to see if a solution is correct, that's pretty easy. You check each row and see do you have a 1 through 9. You check each column, do you have a 1 through 9, and you check each block to see do you have a 1 through 9. And if it works, then you have a solution. But if you want to think just about the rows, you have to check each row for a 1, each row for a 2. So that's 9 checks per row. You might be able to get around with 8 saying, look, if I see that there's exactly 1, 1, and exactly 1, 2, and exactly 1, 3, I don't have to bother checking for the 9. If I had exactly 1 of everything else, I know I'm fine. There's a faster way to solve the Sudoku, at least in terms of writing the code for checking. And again, I'm just trying to do this to illustrate that depending on how you write things, you can make your life a little bit easier. When you typically do a Sudoku, what numbers do you use? 1 through 9. How many of you have ever played the game 2048? where you have the little tiles falling? Yeah, okay. How many of you ever played the NESCAC version of 2048? So we have enough schools.
Sorry, no, I played a different, similar principle. But
Similar
not-
principles, right. And so obviously which school is worth 2? Oh, okay.
Amherst.
I think Amherst often starts as the 2. Or at least the, Williams, yeah, it depends on the game. And which school is the highest tile?
MIT.
Actually, I wouldn't be surprised if MIT hacked into the code and replaced it with their stuff. Either MIT or Caltech would be a likely candidate, but normally you put Williams as the higher tile. Does it matter if we use those tiles with NESCAC schools versus 1 through 9? No, in terms of how we process things, it's a little bit easier. So instead of using the numbers 1 through 9, use 1, 10, 100, 1,000, 10,000, and so on. So now, if a row or column or block sums to 111,000,000, 111,000, 111, the only way that can happen is if you have one of each. Now you just have to do a sum check. And that's a lot easier. And so in terms of how you code things, you can often do tricks like this. When I teach probability, I often give my students questions, and some of you might remember, you have a deck, you randomly deal 7 cards. What's the probability you have at least 2 kings and at least 2 queens? Assign a king to be the value 1, assign a queen to be the value 10. And now you're just seeing, is the sum, does its 1's digit end with a 2 or a 3 or 4? Does its 10 digit end with a 2 or 3 or 4? And you can do these checks much faster. You don't have to put in the whole structure of the deck. You only put in the stuff you care about. Yes?
Did we do a chessboard or is that more of the probability when you showed us this trick?
There's so many of them that you can do. They're all essentially equivalent. I wouldn't be surprised if we did a chessboard.
So wait, for this one, what are we trying to sum up to?
So what you do is you just check and see, does any of the rows or columns or these blocks, they all have to sum to 111,111.
Of a 9 by 9, right?
I'm sorry?
Of a 9 by 9? Or?
Of a 9 by 9.
Yeah.
And the reason is, if you're using as your blocks a 1, a 10, a 100, 1,000, and 10,000, the only way you can get this sum is if you have one of each. If you use the numbers 1 through 9, what does 1 through 9 sum to?
55.
So it's 9 times 10 over 2. So 45. Right? So if I just sum and see, is the sum 45? Does that mean I have exactly 1, 1? No, because I could have all the numbers 1 through 9, or I could have 2 2s and 2 8s, and then the rest being the same. So you want a situation where the sum is unique, that there's only one way to get that value. Do I care if there are multiple ways to get some of the other values? No. I just need that there's only one way to get this number. All right. So this is just a little bit of the theory of how you would actually implement some of the stuff. I want you to be aware when you're writing some of the code, it might occasionally be worthwhile. Take a few minutes and think, how often is this going to be done? How much coding am I going to have to do? Is there a faster way to write things? What part of the problem really matters? What part doesn't? All right, so we are looking at binary integer programming problems. So our random variables now are going to just be 0 or 1. On, off, yes, no. So you want to try to think, what does this represent? Imagine you are an airline. What do you think your variables might represent? I'm sorry?
Flight prices or passenger amounts?
Well, the flight prices would probably be an input coming in to determine how much money you make. So we have variables and parameters. What could, yes?
Whether there's a flight between 2 cities?
Yes, so your variable is probably going to have lots of subscripts. And so you're not going to just have a variable x. So you might have x, C1, C2. Is there a flight from city 1 to city 2, or it matters? Do you want something else? Yes.
Time?
Yes, right? It's not enough that there is a flight. Years ago, I was an organizer at the first ever conference on Benford's Law, and you got to make sure you get there, so you leave a day early. And there was some weather issues, so I called up the airline to just make sure. I said, oh yeah, flight's been canceled. Oh, okay. Were you planning on telling me? Well, your flight's not for a few hours, so we didn't have to tell you. Okay. Do you have any other flights? Yes, there's a flight in 10 minutes. Can you make it? It was a wonderful conversation. I'll skip the line. I'll give cultural extra credit. Boring conversation anyway. Hey, blank, we're going to have company. Cultural extra credit.
I didn't even hear what you said.
Boring conversation anyway. Hey, blank, we're going to have some company. I'm not going to say the name, because if I say the name of the character, it will completely give away the movie. This is a movie you have all seen. If not, heads held down in shame. It is a masterpiece from the 70s. All right. You need to put in the time. All right. It's not enough that there's a flight from city 1 to city 2. You need to know what time. Anything else you might want to put in for the variable? So these are the cities. This is the time. And again, we know how far the cities are, so maybe we know how long it is, yes.
Maybe what type of plane?
Yeah, which plane is flying? Do all the planes fly at the same speed? So maybe this is for the given plane. And then different planes will have different speeds. Their speeds might be a function of the weather. And there's lots of things you can do. But you start to get a sense that when you're doing a problem like this, your variables are not just going to be x, y, z. Your variables have to have a plethora of subscripts that are just singing to you what is being studied. Okay, let's do the movie theater. The reason I want to do movie theaters and not airlines is I actually have published papers with some professors of marketing in the movie industry, and I can actually show you what we did. And the project splits very nicely into different parts. So a huge part of all of this is the data you have. So what do you think happens for demands for most movies as time passes? Goes down. So for most movies, we'll do now movies. And given that the company was in Europe, I will spell theater this way. So this is time since release, and this is demand. So most movies are probably going to be like this. You will have a few movies that are like sleeper hits. So the one I always mention is Blair Witch. No, that was the one that was a big word of mouth. I think Something About Mary was another one like this that started weak and got stronger for a while as time went on. But most movies, people aren't going to be seeing it too many times. There's a few people who will come back and see it. But a bunch of people who want to see the latest Avenger movie or the latest movie in the Star Wars series, whatever. And so there's going to be a huge demand. And once people have seen it, and they might not all be able to see it at the same time, but you're going to have a lot of people who will really want to see it when it comes out. They can't wait. And then the question is, how do movie theaters make money? And we've talked about this. There's the money from the ticket sales, and then there's the money from the concession sales. And when you're trying to figure out how much money you make, you really want to know what is the demand. And depending on what contract you have to enter into, it may not be worthwhile to get a movie that's bringing in a large number of people in the beginning when you get a very little portion of it, if it goes down too quickly and if it's not generating enough concession revenue. Would you rather have a movie that appeals to, say, high school, college kids, or elderly citizens in the sunset days of their lives? This is being because personally, I would like to just make everybody happy. Who do you think is going to be a better clientele for the movie theater?
Elderly people, because they have more time on their hands, I guess.
No, so I'm saying there is no wrong answer for this problem initially. And then once we have data, then there's a wrong answer. But until we have data.
It's really whoever buys more popcorn, but we don't know that often.
In my day, popcorn was 3 cents. And so you have to be careful of, will people actually be buying the concession stuff? Who do you think is more likely to buy? Probably the younger people. Who do you think is going to take more time to clean up afterwards? What's the cost of cleaning up? How much does it tie up the theater to clean up after certain people? So these are the things you need. Yes?
Do you really think younger people are more likely to buy
Yeah. What's the question?
Do you really think the younger people are more likely to buy? I feel like the older people that have money, they can blow $11 on popcorn like a
And they're bringing their own snacks, like, yeah.
Yeah, like,
So, I'm going to be very careful as this is being recorded. You know, of course, we do not advocate in any way, shape, or form people bringing in their own stacks. But if you're on a date or whatnot, are you more likely to be buying something if you're just going out with your friends? So, I'm curious, how many people here have gone to a movie in a theater in the past month? You're not that many people. In the past 6 months. I'm not sure if I've even gone in the past 6 months. I would have to. How many of you have bought concessions?
ever, or?
When the last time you went? So that seems most of the people who went did buy something. All right, how many old people, say over 50, went to the movie theaters in the past 6 months? And how many bought? So look, no old people in our sample set have bought concession revenues in the past 6 months. I think that data is quite convincing. And I believe 50 is a good mark for what we're going to consider old in this class. Mid-40s is definitely still prime of life. Okay? So we need to decide, what do we want our variables to be for the movie theater problem? I'll start you off.
Age.
I'm sorry?
Age. Or time after release, like you're considering how long.
So those are going to be more parameters in terms of how much money the movie makes. We're trying to do our scheduling.
Whether a movie M starts at time T on screen S.
Okay, so just the same notation I have here, I will have screen S, movie M, time T. So this is screen. This will be movie, and this will be time that we start. So 0 if don't start. On screen S, movie M at time T, and 1 otherwise. That's a really good choice of a variable. Now, yes?
Cleanup time?
Cleanup time is going to be determined from the movie.
Why?
So how do you want to view cleanup time? No, this is a legitimate question.
Like how big the theater is?
So is cleanup time going to be a function of the demand of the movie? And if so, then that makes the model more complicated. Or you can just say that there's a fixed amount of cleanup time for movies of different genres. That if it's an action movie, I'm going to just assign 10 minutes to clean up the theaters, or 15 minutes. If it's a romantic comedy, I'll assign 2 seconds. That's not a good assignment, by the way, for a romantic comedy. Yes.
But didn't you contradict that point? It's not so much the movie, it's about timing, it's about the concessions and sales, it's about when you are at that curve. So didn't you already present a point that's actually not?
Well, the question is, how much is it going to gain for you to have the cleanup times variable, and how variable do you want them to be? So for instance, do you think movie theaters are going to have movies starting at 3:14 and 16 seconds, or are they going to do it maybe every 0.5 minutes? So when you look at schedules online, do you ever see movies starting at like 3:17? It's always ending, I think, with a 0 or a 5. So you have blocks of 5. And so this is very similar to a lot of things we do where you have a complicated problem. Do I need to add this level of sophistication, or is this already enough to give a good answer, to give a good approximation of what's going on?
So for this problem, could we just make the assumption that the people planning the movies will have enough time in between so that they don't blow up their own operation?
Well, what you will do is that if you want to then start another movie on this screen, if a movie has been playing, is you have to make sure that you don't start another movie in terms of its cleanup time. So if I start this movie at time T, and let's say it runs for RM, and then you have to put in CM for cleanup time. And then this would be the first time the screen would be available again. So once you start a movie, the screen is not available until the movie finishes, and then you have to allow some time to clean up. The only question is whether or not this is going to be a fixed number for the movie, or if it's going to be variable depending on maybe time of day and demand. You can definitely make it variable depending on time of day and demand. That just makes the model a little bit more complicated. So different types of movies, you might allot different amounts of cleaning time, or you might just say every movie has the same cleaning time. Personally, I would rather just have fixed cleaning times for each movie, and maybe movies that we have historically messy audiences, you just leave more time. But you can easily fix this and have that as a variable as well. So what are some of the constraints you would want to have if you were in the movie theater? I want to see, how do we actually write down the linear programming problem?
Well, you only have so many screens.
Okay. But you got to be more specific. That's not a constraint yet.
The number of screens is a constraint. The sum of the xi's can't be more than the number of screens at any time t.
Okay, so that's definitely one constraint you can use. You can never have, but that just means how many movies start. So we've got to be very careful. I want just the constraint in English right now, not Math speak.
Well, so it's that you can never have more than one movie playing on the same screen
Good.
at the same time.
Good.
So that would then be, I guess.
At most is a better way of phrasing it. At most, one movie on a screen at any t.
Yeah. So I guess you could do that by if you hold.
So the first question is, what the hell are we even summing over?
Some of S, M, and T, or there's even.
Well,
I'm not sure if it's.
Let's fix the time. So we'll fix the time.
Fix the time. Fix
So
the screen.
for all the time, okay, and we'll fix the screen.
And then sum over the movies, and it can be at most one.
So we fix the time and we fix the screen. So this is going to be a huge number of constraints. Now we want to sum over movies. That's the only thing that's left. And then hopefully this is a good notation where capital M is the number of movies in our universe. And now what do we sum over? It's clearly got to start off with an S, M. And then how do I know if movie M is playing on screen S at time t? So this is the hard part. What do our variables tell us? What is x, s, and t telling us? If it's 1, what does that mean? We started the movie on that screen at that time.
So you have to do all the x, s, m, t's for the t's going from the current time backwards.
Yes.
To t minus the length of the movie plus cleanup time combo thing.
So we're going to have a sum. I'll use tau, the Greek tau, and it's going to go from 0, well actually, let me change the order. I want to do the sum of movies first. Because the runtime depends on the movie. And so what I want to make sure is I haven't started multiple movies at the same time. And I didn't start a movie a little while ago and it's still playing, and then I try to start another one. So I'm going to sum over all movies, and then I'm going to sum over all times, going from 0 to the runtime of the movie. And then maybe also add in the cleanup time for the movie. Yes?
What's the left-hand side of what we're getting to? What are we,
This?
what are we trying to calculate?
We're trying to make sure that at most one movie is playing on a screen at a given time. So the problem is, these variables are not telling us whether or not a movie is playing on a screen at a given time. They just tell you when you start a movie. So if I know that this is 1 at time 5 p.m. on screen 3 with movie 2, then it's also, that movie's still going to be playing for some amount of time afterwards. So I have to look at all the movies that could have been started and still be playing on that screen. So let me write it down and then we'll go through it. So it would be x, s, m, and then t minus tau. And we want this to be what? At most 1. So at most 1 is less than equal to 1. And here is the constraint. So what would it mean for one of these terms to be positive? Well, the only values you can take is 0, 1. So if it's positive, it has to be 1. That means that we started a movie sometime either at time t, or t minus 1 unit in time, or t minus 2 units in time, all the way back to t minus the runtime of movie M plus the cleanup time of movie M. So if we started movie M on screen S in this time window, it would still be playing at time little t. So this makes sure that you can't start two movies and still have them both be playing at the same time on the same screen. And for something like this, it does matter which way we write the sums, because the sum depends on the length of the movie. Would it be easy if all the movies had the same length? Oh yeah, much easier. But this is not a big deal. So, RM is runtime of movie M, and then CM is cleanup time of movie M. These are fine. These are easily fixed numbers. So when you're programming this in all the different languages, the professional ones, they would just easily adjust the range of summation. It's not a big deal to handle something like that. Yes?
For the summation, if, let's say we started at time t, which happened to be the time when a specific movie started. So when tau is 0, you get 1.
Correct.
Then if we're going through all of...
So are you saying that this might be a -1 or a +1 up here?
Wouldn't it be less than equal to 2? Because wouldn't we also hit a movie, like if we're going from tau equals 0 to RM plus CM, won't we also, when we're going back in time, by the different time we're...
So this is where it's going to depend as to exactly what you mean by the cleanup time. Is the movie available to be shown at the very end of that cleanup time, or is it not available to be shown until the very next one?
But if we, not even that, but even if we start immediately at t equals the start time, won't we always end up running into a different movie?
So
Maybe I'm not understanding correctly.
I mean, it depends on how you're defining when you're starting and stopping. So are you defining the runtime of the movie to it's still playing at that last block, or that last block is now available for a movie to be shown?
Right, it's running.
So if it's then running, then you can't use that screen until the very next time block.
Okay.
So you have to be very careful in terms of how you write down exactly what the constraints are. So is it still running then, or did it finish and then that's the very next time it's available? So is it available once you've gone RM plus CM, or do you have to go +1 more? So you can, depending on how you want to define things as to when is it available. You could easily have to change these things ever so slightly. You don't want it to be 2, because if it was 2, then you could have 2 movies that started in the same window and then just have a gap before you start anything else. So we really do want this to be at most 1. For the other stuff, you want to be very careful. Since we are not solving the movie problem, I'm happy to just leave it at this level of informality to see what the constraints are.
So you could do plus tau as well. That's just notation, right?
That's just notation.
Okay.
And then I would have maybe tau going from 0 to negative. Because I'm looking backwards in time.
Right, but is there any reason you can't look forwards?
Well, because I'm looking at what's going on at the specific moment t.
Yeah.
So if a movie starts forward,
Oh, okay, yeah.
right?
Makes sense.
So I could have a movie playing right now at time t, and then maybe it plays for the next period, and then it stops. And the movie that starts in the forward time is not going to interact with this. That's why it's better to be backward looking.
Okay.
Okay. Any other questions about this constraint? Yes?
I'm just a little confused. If you were writing this up in a program, you would just exhaustively go through if statements and just see things.
If statements is even worse. We will learn how to do if statements later, but if statements are a huge computational cost. So right now, this must be true for every t for every s. So this is generating a tremendous number of rows of your matrix A. Each pair ts is another row. And this is telling you what the coefficients of A are. For all your variables, not all the variables end up interacting in this constraint. They only interact if they are in a certain time frame of little t. The different screens, the different m's, those can come in.
I know why we can do it, but isn't this matrix going to be massively overdetermined?
No, it'll be underdetermined. you will have many possible schedules that work. Show no movies, okay? Show just one movie, wait till that movie finishes, and then wait 4 periods just for fun, and then show another movie. There's a lot of different schedules that will work. This is an underdetermined system, but if you want to count how many variables you have, well, for every screen, for every movie, for every time, you multiply those 3 together. So we have a large number of variables, and then what's nice is we only have 2 of them coming in for a constraint. So the number of constraints is going to be less than the number of variables. So you can do calculations like this. Typically you do 5-minute blocks. Is it still worth doing 5-minute blocks in the 21st century? 5 minutes is pretty close. How many people still use cash? How many people use cash by choice? Okay. How often do you really use the penny? Is it worth keeping the penny on all these prices, or should we just move everything to 5 cents? Or should we say, you know what? Not only should we keep the penny, but what the gas stations are doing with 9/10 of a cent, this should be expanded. Right? Is it still worth having the penny? There's a cost to making the pennies. And back when I was a kid, it actually reached the tipping point where it was more expensive to make a penny than the penny was worth. The copper was more valuable, and people were just melting down the pennies. And so they moved the pennies to being 97% zinc. And we actually did experiments in chemistry class where you would actually see the zinc and the interactions. They were actually cheap experiments to do given the cost of zinc. But is it worth having that level of detail? When you're doing things online, it doesn't matter because it's all being done. Can anybody give me a movie where they look at the rounding that the banks do and they put it all into their private account? There are 2 movies that would work for that. 2 choices. I'm sorry? No. 2 different movies that would work for that one. The previous one was Han Solo, when they were rescuing Princess Leia. All right. Give me one more constraint. We have yes, we're in conversation anyway. I'm fine, we're all fine. How are you? What's your caller number? What's another constraint we might want to have? I just want to show you how you can do the constraints. Since we're not solving this right now for a company, I don't care about the exact form. These are good concerns that you're raising, and please email me that you raised them. But I just want you to see roughly how we can do stuff like this. I think one of your homework problems might be to design constraints for Sudoku game. You can solve it using linear programming. All right. Can somebody give me another constraint you would want to have for the theater?
There are never there are never more seats sold than are in a given screen, but that involves capacity, which
so we definitely want to have the capacity, and then in terms of trying to figure out what the profit is, you want to look at what is the demand for a movie, what is the capacity of the screen, and if the demand is above the capacity, you actually don't get credit for those. And then the question is, what happens to those extra people? Do they go to another movie? Oh crap, all right, so the new Star Wars movie is sold out, I'll watch the new Avengers movie. Or do they just say, the movie I wanted to see is not available, I'm just not going to go to the theater today. So these are absolutely concerns that you can incorporate. The issue I had with some of my colleagues was whether or not you should deal with movies competing with each other for demand. That there is an action demand that's just fixed, and then you have some people who demand maybe just the Star Wars and nothing but the Star Wars. But what's another constraint we might want to have?
Maybe you don't want to start too many movies at the same time period.
So that's another good one, is that in terms of the lines, you might want to spread out when the movies are starting. And also, you don't want too many movies ending at the same time and having crowd rushing.
You may want to consider how many people you can actually hold.
I'm sorry?
How many people you can hold in the actual theater.
Right, so we were talking about that a moment ago in terms of the capacity. But there's a more obvious one. This is saying you cannot have, let's see, in any screen, at any time, you can't have 2 movies showing.
You can't show the same movie at any 2
You
places.
can't show the same movie simultaneously on 2 screens. Now sometimes, at the same time. But if you have a movie, that movie can be shown on at most 1 screen at a given time. Now sometimes for big movies, you might actually buy 2 copies. And you might have 2 copies of Phantom Menace or Lord of the Rings. So each movie is on at most one screen at a given time. So that's another good constraint. So what would we want to fix now? We would fix M, the movie, and what else would we fix? T. So I give you a movie and a time. How many screens can the movie be on? I'm sorry? One is good, but at most one. It's possible the movie is not being shown. Maybe we got a copy of Pee-wee's Big Top Adventure, and there's just no way we want to show that again. So we would have a sum over what? So this is going to be for all M, for all T, we sum over all the screens, right? And then we want to make sure that we don't have the same movie on multiple screens. So we would probably have a sum, maybe tau goes from 0 to the runtime plus the cleanup time. And then maybe x, s, t, m, t minus tau. So let's see if that works. And we want that to be at most 1. So if we look at what's going on now, we've fixed a movie and a time that we care about. And so we look and see, have we started that movie on multiple screens? Is that movie playing on multiple screens at the same time? So how could it be playing on screen S at time t? Well, it would have to have been started either at time t, t minus 1, t minus 2, t minus all the way up to the runtime and the cleanup time. And so something like this would be that type of constraint. And again, you can see we're fixing M and T, so the number of constraints this is generating us is less than the product of number of movies times number of times times number of screens. So we want to make sure that at the end of the day we have an underdetermined system so that we actually have the chance to optimize, that we have multiple choices. And so you can just keep putting in constraint after constraint after constraint. You can say, I only want so many movies to be letting out in a certain sector of the theater. Or maybe you don't care about how many movies, you care about maybe just how many people are let out. If it's a very unpopular movie, maybe you had to get Phantom Menace for 8 weeks, and this is now week 6, and the demand has gone down. So if it had been in the prime, yes, a lot of people would be getting out, but now we don't have nearly as many people, so it's okay. So you can keep putting in constraints like this. One of the constraints that I told you we had trouble with was the owner wanted a movie to start every 20 minutes. So what you would then do is you would have to say, for every moment in time, I'll do a sum over screens and a sum over movies, and I'll make sure that something started in that 20-minute window. And that just really killed our schedule. And then the question is, what do you want to maximize? So what do we maximize? Profit. Do we maximize things in our canonical linear programming problems? What do? We minimize. Is it hard to go from maximizing to minimizing? Yeah, take the negative and then try to minimize negative profit. Right? I can't write down negative profit and work with that. It just seems absurd. So we'll just write down that we will maximize. But if you were to actually code this, be careful and make sure that you are using a system that is now interpreting this correctly. Did I tell you the stealth bomber joke?
Oh, yeah.
Did I tell you this? Yeah. Okay. So just think about always checking signs and whatnot and making sure. So how would we get profit? Where does profit come from?
Revenue minus cost.
Revenue minus cost. Now a lot of costs are fixed, but some costs could be variable. The more movies you're showing, or maybe the more people coming in, the more agents you have to hire, the more tellers you have to have, the more cleanup crews. You could absolutely include more stuff like that. Right now I'm trying to just do things that are simple. What's one source of revenue? Ticket sales. So maybe we sum over all screens, sum over all times, sum over all movies, x SMT. And then what do we get over here? Yes?
The number of tickets sold.
Number of tickets sold. And so maybe it's going to be the demand of the movie, and maybe the price of the movie. So I'll do it as price. Is the price going to depend on the screen? Maybe, because you might have the luxury, so price could depend on screen, it could depend on the movie, it could depend on the time of day. But that's fine, it's just going to be some fixed parameter. Then you're going to have, this is where you can do it, Max, the minimum of the demand for the movie at time t. If you want, you can even assume the demand depends on the screen. That maybe people are more likely to want to go and see the movie if it's on the special. So we'll have S and T, and then the capacity of screen S times X SMT. So you can't sell more tickets than space. And if you have excess demand, then you have to figure, well, what do I do for the excess demand? Is it just lost, or does it transfer to something else? Yes?
What's the intuition for the min?
You can't have more people in the screen than the room holds.
Right, but what's like the demand variable?
Well, it's how many people, this is not a variable, it's a parameter in the model. It's how many people want to see, so it's demand for movie M at time t on screen S. You might assume that the demand is independent of the screen, but the demand could depend on time of day. You know, if you have a movie that is ideal for little kids, well, when the little kids are at school, it's not going to happen. Yes?
How do you quantify the demand?
You have a theory that predicts what the demand will be for each movie as a function of time of day. And that's the other input to all of these papers, is that there had to be a probabilistic model to estimate. And you would estimate this based on, is this a sequel? Is there a big star in the movie? Is there a hit theme song that's on the air that people are playing? You know, do you think people hearing Let It Go makes them want to see Frozen again because they've heard it on the radio? For a while, maybe. So you have all these improvements. You might say, what is this movie similar to? And so there's a huge, extensive database of ticket sales for movies. You know, trust me, the industry cares about stuff like this. Keanu Reeves, I just saw an article. Who knows who Keanu Reeves is? Right. What was his first big movie? Thank you. Excellent. Email me for cultural extra credit. Thank you. Right. He actually did something that got him into trouble with one of the movie theaters, with one of the movie studios. What did he do?
Turn down Speed 2.
He turned down Speed 2. So I'm not saying anything about Keanu Reeves' intellectual ability, but somebody did look at this kid and goes, no. And he got in trouble with the studio. Oh, we'll replace you. How many of you have ever seen Speed? So you're stuck on a bus, and if the bus goes below a certain speed, the bus explodes. And this movie deserved a sequel, except now they're on a boat. And Keanu Reeves says, no, I'm going to do something else. I'm not going to make Speed 2. The movie theaters want to know, what is this movie similar to? Do we expect it to have a similar success? How do we expect it to fare at the box office? I had Michael Uslan, who you all read listened to his graduation speech. When he came to me, he said, all the action movies now, you have to have this many types of toys. Because so much of the movies is now about the sale of the material. So this is the start of how you would calculate your profit. And you would add to this concession revenue. And the concession revenue is going to greatly depend on the demand of the movie. All right, this is a good place to stop. I will